So the next item is sandboxing. So we have untrusted code that we wish to run. For example, you downloaded a program from the internet, such as the toolbars or the viewers or even the codecs, etc. But the source of this code cannot be trusted, and as you will see in a few labs later, it's very easy to repack a program with the malicious code appended to it. So, and it is in general, people do not really check the checksum values. So a legitimate provider will provide a checksum value so you can check that, but in practice, not many people actually do that. Okay, so we need various ways of trying to protect our system from untrusted code. So we should really contain that code in a zone such that if it does misbehave, then we can easily kill it without that malicious behavior being spread onto different processes and different regions of our system. Okay, and creating that zone by confining, restricting the access outside is what we call sandboxing. Okay, so the confinement is to contain the application in an isolation and make sure that it does not carry out unapproved actions, especially onto the places where it shouldn't be doing stuff, like into the memory spaces or in the privileged files, etc. And the sandboxing can be implemented at different levels of the system. For example, we can even have a hardware sandboxing, basically running the applications on different hardware. But this can be quite costly to afford all the hardwares we need to support. A little bit higher level up is the virtual machines, where you create a whole operating system on a virtualized machine. And so it runs and does the same thing as a typical computer, but the whole virtual machine has been locked, has been isolated from the host computer. A little bit higher level up is the system called interposition, where the processes in a single operating system can be isolated. A little bit higher up is the software fault isolation, so we're looking at software level sandboxing, where different threads sharing the same address can be isolated using some techniques. We'll have a look at it. And application-specific sandboxing is also applicable here. For example, browser-based confinements for different web pages that you visit. So in this particular, we will look at those two, the system call interposition and software fault isolation. So for the system call interposition, one of the techniques is to use chroot. Okay, and this is often used for guest accounts, where the guest accounts, a guest user onto this particular computer can do their things, but they shouldn't be able to fiddle with the system components, the files, and configurations. So you're trying to confine the user space on the same computer, so they can still do some things, but does not have privilege to escape to outside. So this can be created. So we can create a chroot onto the /temp/guest, and this will form the root directory for the guest. Okay, and we can now switch user to the guest, which will set the user to the guest. Okay, so the path, the /temp/guest, is going to be now added to the file system for the applications in jail. We call it a jail to isolate all those things that are happening with the guests to be within the boundaries that we set. Okay. In order to set up the chroot, you will require the root privilege to do so. Okay. So the problem is utility programs also need to be available in jail. For example, the commands that we use in the terminal, like ls, ps, vi. Okay. And if you don't have the right privilege set or the access, then the guest user will ultimately have to either reinstall all of these, which is going to be very difficult task. So the layout of the directories or the access level kind of looks like this. So we have the root directory with our normal other directories like the user bin, etc. Okay. And within there we have the new root, which also contains the user bin, etc. And the key idea is whenever the guest user within its own space trying to escape the root, the access is denied. So the whole idea is to confine the access of applications that are trying to access outside, and because of that, we cannot access some of those like common commands within the guest. So in order to provide those commands to the user, the guest user, things like the jailkit can be used to address this problem. So what it's doing is it auto builds files, libraries, and directories that are needed in the jail environment. Okay. So we can create the jail environment, check jail environment for security problems, things like any modified programs, world writable directories, etc. And we restrict the shell to be used only within the jail itself. So that toolkit can be quite useful to allow such guests to access those common commands. But of course, people will always try to break out of jails. So here's a scenario where we specify open ... etc. password. So what we're trying to do is trying to escape our jail. Okay, so if we go up 2 steps up to the root, now we can access the etc. folder here. Okay, and maybe etc. folder will contain some passwords that we're trying to read. If configured fine, then this access will be denied. But scenario 2 can also work. Make directory, some random directory called password. We're going to chroot the ASDF, then we can escape the jail. Okay. And this can happen if the process has a root privilege, then you can escape. So in scenario 2, what we are doing is, if scenario 1 failed, which means you didn't have the root privilege, scenario 2, we're going to grant the root privilege onto the folder ASDF. Okay. So once we have granted a root privilege, then we can escape the jail using such sequences down here. Okay. So in a nutshell, chroot can be used as one of the solutions to try to isolate the guest users from the normal system, but it lacks many capabilities. It's either all or nothing access to the file system, which is not very useful for web applications. It also needs to provide access to files outside the jail. This is where the problem is starting to lurk in, where you need to grant some certain privileges for the guests to access them. And malicious applications can access the network still. Okay? And do something with other internally connected machines. So you don't have to particularly compromise your host. You can jump back to other hosts within the network, exploit that, and come back to the host machine. Okay? So there are various design flaws associated with the chroot. So in a nutshell, the suggestion is to not use the chroot as a security solution, but rather just understand that such things exist. There are better approaches and combinations of other approaches that should be used in conjunction to provide security. So the next one is the software fault isolation, short for SFI. The problem is the legitimate and malicious applications can run in the same address space. For example, the device drivers trying to corrupt some kernels. Okay, so the solution is to isolate those softwares by separating applications into different address space. And instructions are added before the memory operations and verify their behavior prior to being running. For example, make sure that those applications do not try to attempt to access the memory illegally. So let's have a look first how applications are laid out in the memory space. So partition process memory into the segments. So you have the code segment, the data segment, code segment, data segment, etc. for different applications inside the memory. So we're trying to locate unsafe instructions. For example, there are some assembly code that does the jumps or load or store, and those can be used quite maliciously within the applications, trying to corrupt some other parts of the memory. So we want to add safety instructions for the memory access and add guards before unsafe instructions at compile time. So during those code gets compiled, those guards are added so that those guards will be in place prior for running the code segment, and we can validate the guards when loading those applications. So here's a brief example of adding the guards. So firstly, we're going to reconstruct the code instructions for safety. So there are various untrusted code that could be identified, which should only be able to jump within its domain's code segment and write within its domain's data segment. So if the code has some commands that tries to jump outside, then maybe it's trying to corrupt some other memory spaces, as well as trying to write outside the data segment, which means it's trying to write some malicious stuff outside the boundaries of its applications. So the unsafe instruction, for example, is this example here. We're going to store R1 into a location of R0. Okay? But the memory location of R0, if the code can specify it, then we have to make sure that the boundary checks are done. So we can rewrite the instructions by the sandbox. Okay? So first we're going to copy R0 into RA. Okay? And then we're going to get the segment ID, make sure that RB equals RA. And then we're going to hold the data segment ID inside RD, and then compare it to the RB that we just checked the segment ID with. And then if the IDs don't match, then we're going to raise a flag as a fault. And finally, we can then store R1 into RA, because if there's no fault flagged, then it's safe that the location RA is within the application memory space. So we can write R1 into RA. You don't have to fully understand what these commands do, but get a basic idea of what's happening at an assembly level when the application gets loaded onto the memory. So rather than trying to copy over R1 to R0 in the memory space, we are adding some safe precautions before we do that. So essentially what's happening here is to add the guard zone prior to and after the code segment and data segment, which can be used to ensure that when we are looking at the instructions here, that they are within the boundaries. And typically this will add some extra spaces before and after the segment, but normally it's quite small relative to the size of the code and data segments. So once we add the guards and add those check codes, assembly codes, the verifier ensures that all instructions are safe. So that was one example for the store. We check all the other instructions that are associated with the application, and if it's found to be insecure, then we're trying to add extra secure payloads on top of that. And the verifier also checks no privileged instructions are in the code, as well as that those instructions are within the code and data segments. This can be checked against the boundaries. And if the sandbox code fails any checks, then the verifier will reject the code, and hence the application will stop working. So this ensures that all the instructions within the application gets checked to stay within the boundary itself, so it cannot access outside the confined boundaries. And this has been working fairly good, but there are some limitations to it. So here you can see that the overhead is roughly about 4% in processing time, which is quite practical in a sense. But this is quite difficult to implement in the 86 architectures. It is designed for the 64 architecture in the first place. And also you have to actually write this for different architecture designs as well. So the portability is a bit of an issue where you have to manually set how the guard can be generated for different applications for different architectures. There have been some research where the guards can be generated dynamically, as well as ensuring the assembly codes instructions are safe, but there's always extra things that can be done. So in summary of the sandboxing, there are various techniques for sandboxing in different layers. We had a look at two in particular within the system itself and at the application level. It is difficult to fully isolate malicious code due to dependencies, as we've seen with the CH root, because even the guest user would like to use certain basic applications, and trying to grant that access from the host can leave some holes where the guest can escape the jail that has been created. And the same thing is for the SFI, where the guards have been introduced to confine the application within its own memory space, but at the same time, it's quite difficult to implement for all the architectures out there. So the good practice is to consider various sandboxing techniques in conjunction with other security techniques, and make sure that defining sandboxing policy is one of the top key defining the sandboxing policy well to ensure that no such jailbreaks or escaping the memory space is possible. However, defining these policies really well is one of the key challenges that we face today for the sandboxing. So we will stop the sandboxing items here. If you have any questions, just let me know. Next up is steganography.